Hey, this is Mark Carrion. I'm going to put a video out for Boyle's, Charles, and Gay-Lussac's law to help you guys through those problems that we had kind of started when we went on hold here. So I'll be putting out videos for all the notes that I'm giving you guys. There'll be another one coming out soon for the ideal gas law and some of the other ones. And, if you have questions, send them to me. Do the best you can for right now. Watch the videos, look at the notes, do the gizmos, look at the homework practice. Just keep yourself sharp on this stuff as we go. Okay, so Boyle's law, real easy. We talked about this in class, but if you're gone, this will you're going to remind everybody, review it a little bit here. But the Boyle's law equation is P1 V1 equals P2 V2, which is shown here. As the pressure goes up, the volume will go down, and vice versa. If the pressure drops, the volume goes up. So temperature is considered constant in this one, which means not changing. So if you're doing an experiment with Boyle's law, like our gas chamber at school, the temperature in the room is not changing. It's just those two things, pressure and volume, that change. Because one's going up and one's going down, we call that an inverse proportion. Okay. And again, think of taking a sealed chip bag up to the mountains. If you haven't done that before, the bag gets bigger because the pressure up in the mountains is lower. So the pressure inside the bag will push out, to push out into that low pressure. So that's a really good example of it. For the math examples, we got a couple things going on here. We have, a gas and a balloon in this one, and consider a balloon as a flexible container. It can change volume. And that's a good indication that it's a Boyle's law problem when that can happen. The other indication is that we start at 10 liters, which is P1, and we're going to end up finding a new volume. So in this one, it's we have V1, which is here. Sorry, not P1. We have another first pressure, which is P1, and I just label that. And I know they're both ones because they're tied together with the word and. Okay. The balloon is taken up to the mountains where the pressure is 0.9 atm. Okay. Notice the pressure is dropping. And it says, what is the volume of the balloon up in the mountains? Once I identify everything, this is P2. Once I identify all the variables, all I got to do is plug them in. But before I do that, I need to do the algebra on this thing. So we got to get V2 by itself. That means you're going to have to divide by P2 on both sides, and we end up with this equation. Okay. Once I have that, I start plugging stuff in. I go back up here. I said, oh, there's P1. I'll put it right there, and you notice it goes there. I look at the 10 liters here. That's V1, so that's going to go there. And the 0.9 atms would go down here. In the calculator, it's always multiply the top, divide by the bottom, as you guys know, and you get 11.1 liters. Now notice that the volume went up as the pressure went down. We're just going to do this. The volume went up. Okay, inverse proportion, the answer makes sense. It should go up. It went up a little bit. We're good. Okay, let's look at another one of Boyle's. This one's solving for pressure. So it works the same way. We have a gas with a volume of 400 milliliters. So I'm going to look at that and I'm going to think, okay, that must be V1. So I'll mark it as V1. Now, that one is in milliliters. It doesn't matter if they're both in milliliters. Notice the 200 down here. Same unit, they cancel out, as you're going to see. These guys, the volume is starting at 4 atm, which is P1. We go down here and it says the gas is moved to another location with a different pressure and the volume goes down to 200 milliliters. So that's going to be V2. So it's asking what is the new pressure, and the new pressure in this case is P2. So we solve for P2, which you see here, and we again plug in the numbers. Go back up to your question, figure out where everything is and put it in its proper place. Do the math. 4 times 400 divided by 200 gives me 8 atms. Now, here's what happened with this one. In this one, the volume definitely went down, and you notice the pressure went up, and it was an inverse proportion. The volume went down to half of what it was, and the pressure doubled. That is what we mean by inverse, and that's, again, a Boyle's law problem. Boyle's law problems are the inverse proportion problems. Okay. All right, let's look at Charles' law, which we sometimes affectionately call Chuck's law, as a nickname for Charles. So Chuck's law, as temperature increases, the volume is also increasing. So you notice that we have two things doing the same thing. We call this proportion direct. Okay, you put a balloon in the oven. If you put it in a low temperature, like 170, that balloon's going to get bigger as it sits in there. Now, it says the pressure stays constant. With Charles' law questions, if that pressure is going to stay constant, that must mean that the container is flexible. So we're looking again at balloons. And when it's flexible, you're looking at a Charles' law question, because the pressure will not change inside there if that's happening. Okay. So let's look at a math problem for Charles, see how that works. In the notes, remember to watch the videos. You know, if anything, it's Crazy Russian Hacker will make you laugh. But he does the liquid nitrogen and the balloons video here. That's pretty good. So definitely take a look at that. Charles' law math example. Okay. Here we have a gas that has a volume of 2 liters and a temperature of 25 Celsius. Remember, when you're working with gas law problems, you never use Celsius. Get that thing into kelvins. So to get the kelvins, again, it's 25 degrees Celsius plus 273. That's a C. I'm writing with a stylus, and that's a plus, believe it or not. There's a 3, and you add those guys together, you get 298. Now, this one's asking for volume, so we take our equation. We got to move the T2 up there. Don't tell your math teachers we're not, spending a lot of time on this. All you got to do is take it down there, bring it up to the top. We get the solved equation there, okay? And then we start plugging stuff in. Now, the 2 liters is V1. The 25 Celsius, which is 298, is T1. And the 50 plus 273 gives me T2, and T2 goes in the top there. So that's the 323 is coming from 273 plus this 50. The 298 we already calculated goes down there, and the 2 liters there. Do the math, multiply the top, divide by the bottom, you get 2.17 liters. Now, let's figure out if this answer makes sense. We started at 2 liters at 25 degrees Celsius. We went up to 50 degrees Celsius, and notice that the volume also went up. So the temperature went up and the volume went up, which means direct proportion. The answer makes sense. We're good to go. Okay. Let's look at another one. Okay, so here's a second version. Now, this is where things get a little tricky, and you got to be careful. Okay. This one's asking for the temperature in Celsius. So if that temperature is the new temperature, then we're looking at T2. So we start off with our Charles law equation. And again, these are always given to you. You don't have to memorize them. Whenever you get a question that's asking for something on the bottom, flip it first. So I took that equation and I inverted both sides of that equal sign. Notice that it's flipped. And now the T2 is on the top. How do I get the V2 out of there? We take it and move it up there. And this is how we get our equation set up for that. If you don't do that extra step of flipping it first here, you're going to get an answer that is the inverse of the actual answer. It's going to really screw you up, because if I solved for T2 without flipping it here, the V2 would go down there and I'd end up with a 1 on the top. And that's not the answer. It's 1 over T2. We're looking for T2. Remember the analogy I gave you guys earlier in the year? If I give you 1 over $4, you're getting a quarter. But if I give you 4 over $1, you're getting $4. Okay, they are not the same thing, and neither are these if you don't flip it correctly. So whenever you're looking for temperature in these problems, any of the 3 problems we're looking at here, if it's temperature, flip it first. Okay, if it's on the bottom, flip it first. Okay. Going through the problem, it's already in kelvins for the temperature, but we have a V1 and we have a T1 and we have a V2. We plug all those guys in here. We get 660 kelvins, but the question doesn't ask for it in kelvins. It asks for it in Celsius. If it asks for it in Celsius, do not solve the problem in Celsius. Never, ever solve the problem in Celsius. You solve it in Kelvin and then convert it back, okay? So we get 660 Kelvin. Now, if you're going backwards to Celsius, subtract 273. We're going to get 387 degrees Celsius at that point. So that's a second type of Charles law problem. That's when you're solving for temperature, and that's on the bottom. If it's on the bottom, flip it. Okay. Let's go to the next one. This is Gay-Lussac. The name gets mispronounced on a regular basis. The French pronounce this Guy and Lussac. Okay, so Gay-Lussac's law relates pressure and temperature. Notice what's not in there. It's volume. Okay, so volume is constant in this one. This means the container is rigid. So imagine a hairspray can. Those things are under pressure. You stick them in a fire. The volume cannot get much bigger than it already is. We consider that a rigid container. In reality, it does flex as it gets hotter, but in our questions, we're assuming that's not happening. It just breaks. Okay, it explodes. So throwing a hairspray can into a fire is, really stupid because it's going to explode, and that's due to Gay-Lussac's law. Notice the proportion is direct. Anytime they're on top of each other like this, and like in Charles' law, it's a direct proportion. Okay. Highly recommend watching the video of this idiot putting one in a fire. Okay, not to name call, but it's pretty dumb and dangerous. Gay-Lussac's law math example here. Let's look at one. This one, it says you have gases in a spray paint can, and they're at a pressure of 4.75 atm and a temperature of 25 Celsius, about room temperature. Remember, do not work the problem in the Celsius. You got to get that into Kelvin. Okay, so that's 298. We did one like that earlier. Temperature is raised to 100 Celsius, so get that into Kelvin, which is 373. Okay, the pressure needed to burst the can is 13.6. Now, that is not going in the problem. What we're trying to figure out is, are we going to get to that pressure with this problem if we get up to 100? So we've got Gay-Lussac's law, and we're solving for the pressure, P2, which we don't know. We plug in all the stuff from up above into our equation, and we get an answer of 3.79 atm. That's the pressure that's going to be in the can when it gets up to 100 Celsius in that fire. Now, what's going to happen to the can at this pressure? If it explodes at 13.6, then nothing's going to happen to this. So the can, it's an absolute no that it's going to burst at 100 degrees Celsius. Now, in a real fire, it's going to get way hotter than that, but we're just saying at this temperature, what's going to happen there, okay? So, and we're not even sure if this is being thrown into a fire at that point. So that's a Gay-Lussac's problem, okay, that we have. Here's another one. This is a Gay-Lussac's looking for a new temperature. If the temperature is on the bottom, and it is in these problems, what do we have to do first? We have to take our original equation and do this. We need to flip. Okay, so flip that thing, both sides, then solve for T2. Okay, so the P2 ends up on the top here, T1, P1, and we're solving for T2. Anything Celsius, get that into Kelvin. 20 plus 273 is the 293 that you see there. The 3 atm, is pressure 1, and the 1 atm, the 3 atm is pressure 2. The 1 atm is the pressure 1. Okay. Remember that this and ties the temperature, which is T1, with the pressure here, which is P1. And then that must be pressure 2. So that's going to go on the top in this setup because pressure 2 over here is on the top. Okay, so we do the math. We get 879 Kelvin. The question, be careful, is asking for it in Celsius. 879 minus 273, 606 degrees Celsius. You notice this thing went from 20 to 606 just with the pressure rising by 3 atm. Okay, so you can change the temperature of a gas by changing its pressure. And that's what Gay-Lussac's, is all about, is the pressure and the temperature. Okay, so a couple of things here to kind of look at here at the end of this video for today. If you look at the different laws, here we have graph A, which is pressure and volume. Pressure and volume is Boyle's law. And you notice with an inverse proportion, we get a graph that looks like this. And it's a curved graph that does that. Okay, it's because it's inverse that's happening, and it's going down because as one goes up, the other one goes down. Okay, look at Charles' law. We have volume and temperature. Notice it's a direct proportion, meaning they're both going up, and you get a graph like that. And the Gay-Lussac graph is exactly the same. It goes, as one goes up, the other one's going up in a direct proportion. If this doubles, the temperature in Kelvin will double. Now, again, those temperatures are in Kelvin. With volume, if the volume doubles, the temperature is going to double. Okay, and vice versa. So with pressure and volume, as one goes up, the other one goes down, but it's an inverse proportion, so it's the reciprocal. So those are the first three gases we talk about in here, and you can work on that first gizmo with that knowledge, and also any of the homework assignments that are given to you guys. Hang in there. It's going to get better, but there'll be more videos coming as I make time to get these done. You guys will see more coming up. So just be on the lookout on Google Classroom for what's going on, and the calendar on Google Classroom for you guys. Okay, take it easy.